In this video, we're going to see light emitting diode. In short form, it is called LED. As the name tells that it's a diode, PN junction diode, which emits light. Now, before seeing how a diode can actually emit light, let us see how can a semiconductor basically emit light. If you take an energy band diagram of a semiconductor, it would look like this, where we have conduction band and valence band. Electron in conduction band, when it makes a transition to valence band to recombine with the hole in the valence band, the energy that the electron has lost would be emitted in the form of light, h nu, if the semiconductor is direct bandgap semiconductor. If it is non-direct bandgap semiconductor, then it wouldn't be resulting in a radiative recombination. Instead, it would be non-radiative and would result in heat energy. Which means if you're going to talk about a diode which can emit light, then that diode should be made with a direct bandgap semiconductor. And of course, silicon and germanium are not direct bandgap semiconductors. So we cannot make the diode with silicon or germanium. And in fact, we can make with gallium arsenide, which we discussed was a direct bandgap semiconductor. The energy of this emitted light, the photon, would be approximately the Eg, energy bandgap between the EC to EV. And if you take Eg in electron volts, it can be written as 1.24 over lambda, assuming lambda is in micrometers. Color of the emitted light would depend on the wavelength, and the wavelength would depend on the energy band gap Eg. So in order to get a particular color, we need to choose semiconductor material matching the energy band gap. So first point, we mentioned that the semiconductor should be direct bandgap semiconductor. And in this recombination, we are basically not stimulating for the electron to actually recombine. It is happening spontaneously. So we call this recombination as spontaneous recombination, and the emission as spontaneous emission. And we also said color of light depends on the wavelength lambda, and lambda depends on the energy band gap of the semiconductor we choose. Now, if you take a PN junction and apply forward bias, then majority carriers holes from P side would get injected onto the N side, and as they diffuse in N side, they recombine with the majority carriers there, electrons. So there would be electron hole recombination close to the junction. And at the same time, electrons would be injected onto the P side. As these electrons diffuse in the P-type material, they recombine with the majority carriers there, holes. So you have electron hole pairs recombination near to the junction on P side as well. If this PN junction is made with a direct bandgap semiconductor, then this PN junction diode would be emitting light. In terms of energy band diagram, when we apply forward bias across the PN junction, we have the barrier potential as Q times VBI minus VD. Where VD is positive, then the barrier potential would decrease. As a result, electrons would be injected across the depletion region, and similarly, holes will be injected across the depletion region. As they are injected, they can recombine and give rise to radiative energy h nu, and they can do here or even here and here. From this minority charge carrier distribution under steady state, we can understand that most of these minority carriers are recombining near the depletion region, which means most of the recombination would happen at or near the depletion region itself. As a result, light generation inside the PN junction would be at or near the depletion region itself. When you increase the current flowing through the PN junction, there would be more recombination of carriers. As a result, there would be more light energy inside the PN junction diode. Now we will discuss one important parameter in light emitting diodes is the external efficiency, eta ext. External efficiency tells us how many photons came out of the PN junction diode to external world with respect to how many electron holes have actually recombined. Eta external can be written as internal radiative efficiency times extraction efficiency. Internal radiative efficiency tells us out of all the electron hole pair recombinations, how much percentage of these recombinations were radiative in nature. Even though we are saying a direct bandgap semiconductor, it's not all the recombinations would be radiative in nature. Most percentage would be radiative in nature. Some would be non-radiative as well. So this internal radiative efficiency talks about that efficiency. So which means out of all the electron hole pairs recombining, there is only a fraction of them actually resulting in light. Extraction efficiency tells how many of these photons are generated inside the p-n junction diode and how many of them had made it out of the p-n junction diode to the external world. This parameter depends on the quality of the direct bandgap semiconductor we are talking about. It's all about getting a good quality direct bandgap semiconductor. And second, extraction efficiency basically depends on multiple factors. The light that is generated, if you see, it generates energy of h nu. And in fact, that energy is exactly equal to an electron needs here to actually go to conduction band, which means this light energy can be absorbed inside the p-n junction itself. So this is called reabsorption, and it is actually a loss that is actually captured by this extraction efficiency. And another thing is, this light can be going in any direction. If it actually goes in a particular direction, outside environment to this p-n junction diode, refractive indices would be different. As a result, we might have a total internal reflection. So this light basically stays inside the p-n junction and eventually can be absorbed inside the p-n junction diode itself. In fact, that is one of the reasons why we find LEDs with dome type encapsulation, which acts as a lens so that more of the photons can be extracted. And now coming to applications, LEDs are used in digital displays and traffic and automotive signals. For red light emitting LED, gallium arsenide phosphate is used as semiconductor, and for green LED, gallium phosphate is used, and for blue LED, indium gallium nitrate is used as semiconductor. A point to remember that LED should be forward biased to emit light. And this is how a light emitting diode's symbol would look like, where this is anode and cathode, and this symbol looks exactly same as a normal p-n junction diode, except that we have two arrows here, indicating that this diode is capable of emitting light.